Welcome. In this lesson we continue 4.2 and we talk about the second derivative test. We will use the second derivative to locate local maxes and mins of a function. First, let's talk about concavity and inflection points. A graph has a certain curviness to it in different areas, and one of the sides of the curve is the concave side. Sometimes the concave side of the curve faces up, and sometimes the concave side of the curve faces down. So I can separate the curve into different sections that are concave up and concave down. The first section is concave down, and then it changes to concave up, then concave down, then concave up, and then finally concave down again at the very end. And I'll just abbreviate these CD, CU, CD, CU, CD. We can find those points where it changes concavity. Those are the points on the curve itself. And those are the points on the curve where the curve straightens out the most. When the curve straightens out and then changes concavity, that is an inflection point. So this curve has 4 inflection points, the division points between where it's concave up and concave down. The second derivative tells us where a graph is concave up or concave down. Let's see how that works. I have 4 graphs here, and I want to know the original function, the first derivative, the second derivative. Are they positive or negative for each of these 4 graphs? Maybe pause the video now for a couple seconds and see if you can answer those questions. First derivative, second derivative, are they positive or negative? All right. Coming back, assuming you've paused the video and given it a try, let's answer these questions. The original function f for all of these is positive. That's because the graph lies above the x-axis in every case. Now what about the first derivative? The first derivative tells us increasing or decreasing. That was in a previous lesson. In the first 2 graphs, the function is increasing. In the second 2 graphs, the function is decreasing, and so now let's take the second derivative. What does the second derivative tell us about a graph? It tells us concave up or concave down. In the first graph, what's happening to the first derivative? It starts off with really steep positive slopes, and then the positive slope becomes a little less, and then at the end I still have a positive slope, but as a smaller positive number. That first derivative is decreasing. So how is the first derivative changing? It is decreasing. So my second derivative is negative, and this graph is concave down. Look at the second graph. In this picture, I start off with positive slope, but then that positive slope increases. It goes from small positive to big positive. So my first derivative is increasing. My second derivative is positive, and the graph is concave up. In the third graph, it starts off with negative slope, very low negative slope. And then as we move to the right, that negative slope still stays negative, but it becomes less negative. It's increasing. The slope is increasing. My first derivative is increasing, so the second derivative is positive, and the graph is concave up. Let's turn our attention to the fourth graph. It starts off with negative slopes, so the first derivative is negative, but those negative slopes become even more and more negative. That first derivative is decreasing, and so the second derivative is negative, and the graph of my original function f is concave down. So there's this tight connection between the second derivative being positive or negative and the graph of the original function being concave up or concave down. See if you can sketch a graph that has the following properties of its first and second derivatives. Pause the video now, take a couple seconds, see if you can figure it out, and then restart when you're ready to see a solution. Alright, let's draw some axes here. Now, from negative infinity to 0, so on the left part of the graph, we need a function where the first derivative is positive and the second derivative is positive. So the function f is increasing, and it is concave up. So the graph to the left of 0 looks something like that. To the right of 0, Our first derivative is positive, the second derivative is negative. Oh, so the function is increasing, and f is concave down. What does that look like? Increasing, but concave down. All right, so it needs to start off increasing concave up and end increasing concave down. So maybe something like that, where the inflection point is right on the y-axis. Increasing concave up, then switches to increasing and concave down. There's one example of a natural function that has this property. That's the tan inverse function. Looks that way. Let's tackle a function given to us symbolically. This function, 1/3 x cubed minus 3x squared plus 7x, where is this function concave up? Where is it concave down? Basically, I need to take the second derivative and figure out where's my second derivative positive? Where's the second derivative negative? All right, let's begin. How about the first derivative? All right, and now the second derivative. Okay, let's figure out where the second derivative is positive or negative. The first step of that is to figure out where it's 0. So let's solve f double prime of x equals 0. So now I can make my sign chart. I'll put 3 at the bottom, and I want to figure out f double prime of x. Where is that second derivative, positive or negative? Well, it's 0 at 3. I'm looking at my second derivative. If I plug in numbers greater than 3, those values are positive. And if I plug in values less than 3, those values are negative. So my original function f is going to be concave down before 3 and then concave up to the right of 3. And then, for what it's worth, there is an inflection point at the point 3, f of 3, whatever f of 3 turns out to be. And this brings us to the second derivative test. Suppose that we know that the derivative at some critical point is 0. How can we determine whether that is a max or a min? We had a way of using the first derivative in the past to do this. We would draw a little sign chart, put down the c, and I'd look at my first derivative and determine, is my first derivative negative or positive around that c? At which point I could tell if my original function f was increasing or decreasing, and I could determine whether there was a max or a min there. Well, instead of using the first derivative and testing around points, what we can do is use the second derivative and evaluate the second derivative at that point. If f prime of c equals 0 and f double prime of c is greater than 0, then there's a local min. My second derivative being greater than 0 means the function is concave up. The first derivative being 0 means it has a horizontal tangent. Second derivative being positive tells me it's concave up, and so it must be a min. Similarly, if the second derivative is negative, the original function is concave down, and it must have a local max at that critical point. And lastly, if my second derivative is 0, we can draw no conclusion. Let's do one last example, and we'll see how this works symbolically. Suppose f of x equals x times e to the x. The first derivative, it turns out, is 1 plus x times e to the x. And let's suppose that we figure out f prime of negative 1 equals 0. So negative 1 is a critical point. Is that a max or a min? Let's use our second derivative to figure it out. Now that I have my second derivative, I want to evaluate the point negative 1 at my second derivative. F double prime of negative 1. And I don't actually care what the answer is. All I care about is it positive or negative? So when I plug in negative 1, I get positive 1, e to the negative 1, which is e to the negative 1. And e to the negative 1 is a positive number. Positive. So my second derivative is positive, which means the function f is concave up at x equals -1. Concave up, little smile, it means there must be a min. So f has a min at x equals -1. Okay, you have the tools now to do the homework problems. Give it a try. Let me know if you have any questions.